molecular peak is quite weak. This is because the ionization makes the carbon-nitrogen bond length longer, and thus the bonding is weaker. For the experimental mass spectrum, we do not observe this molecular ion peak. This is because high energy electron impact creates high energy molecular ion, which can very quickly dissociate. Okay, so the final application would be for the polymerization of cyclohexane by TDSM calculations. So cyclohexane has attracted much attention because it can be used as silicon sources to prepare silicon-containing materials such as silicon nanorods, silicon thin films, through liquid-based methods. CHS is also a good alternative to traditional monosilane in chemical vapor deposition technique. So the preparation of cyclohexane, the preparation of silicon containing materials using cyclohexane follow a general chemistry. So basically, due to heat treatment or UV treatment, the cyclohexane can transform into hydrogenated polysilane through ring opening polymerization with additional thermal treatment. There are several bond breaking events, such as the breaking of silicon-silicon bond or breaking of silicon-hydrogen bond. So we end up with amorphous silicon. So the amorphous silicon can also transform into crystallized silicon with additional heat or laser excitation. So the ring opening polymerization has been captured by the experimentalists, but still the theoretical study is not available. So to better understand the photochemistry as well as to design more efficient fabrication methods, it is necessary to perform theoretical studies. So we want to model ring opening polymerization of liquid cyclohexane, but it would require huge amount of computational resources, so it is not realistic. Instead, we model an oversimplified model. This time, our simulation cell consists of 2 CHS molecules, and we consider 2 placement configurations, face-to-face and side-by-side. And we compute the absorption spectrum for both of them. And here is the result. And we found there is no absorption in the visible range. This picture shows the liquid cyclohexane, and we can see it is transparent. So this means our calculation is in qualitative agreement with experiment data in terms of absorption. And from absorption spectrum, we can find 3 specific transitions, and these transitions are used in TDSMD calculations. So here I show the trajectory of TDSMD calculations based on face-to-face configuration. This is unprocessed trajectories, which means the intermediates are still hot. So for the first half of the simulation, the kinetic energy accumulated is quite small, so we only observe limited reaction events. We only observe the breaking of silicon-hydrogen bond. So we find rich reaction events in the second half of the trajectories. So we can observe the breaking of silicon-silicon bond. We can see the breaking of the ring structures. Okay, so the dimerization happens at the very last stages of TD-SMD trajectories. So next we analyze the properties of cold intermediates. Here I show some examples. So at 1626 femtosecond, we can see the formation of dimer. At 1980 femtosecond, we see two hydrogens are ejected from the dimer. And in the middle, we have a special silicon. The coordination number for this silicon is 4, so which is typical in amorphous silicon. We also find the band gap decreases with increasing of reaction time. So initially, the band gap is about 5 electronvolts, but the band gap for the final product is about 2 electronvolts. So we also calculate the emission spectrum for these intermediates. What we did is we perform additional adiabatic molecular dynamics at room temperature based on the cold intermediates. And here is the equation for the emission spectrum. So this equation accounts for fluctuation of quantum orbital energies due to thermal motion of nuclei. By using this equation, we assume there is instantaneous relaxation of any excitation to the lowest excited state. So basically, we assume emission is always from LUMO to HOMO. From this figure, we can see red shift and also the light width broadening. Okay, so finally we can build a simulated mass spectrum. So the dominant peak is the monomer, silicon 6, hydrogen 12. For the first spectrum, we also observe the dimer peak, silicon 12, hydrogen 24. But this dimer peak is missing for spectrum B and spectrum C. So this is because for the simulation starting with face-to-face configuration, dimerization happens before dehydrogenation. But for simulations starting with side-by-side configuration, dehydrogenation happens before dimerization. In addition to the monomer peak and the dimer peak, we also observe other species. So species at the left correspond to fragments with molecular weight less than the monomer, and the species at the right corresponding to fragments with molecular weight higher than the monomer. So basically, this part can be understood as fragmentation, and this part can be taken as polymerization. Okay, so to conclude, TD-SMD calculations predict reasonable distribution of fragments, and also TD-SMD has potential to model a broad range of photoinduced chemical reactions, including photopolymerization. Yeah, that's it.
Okay, thank you. So any questions are very welcome, because in physics seminar, audience will not sit silent. They will stop during the first 3 minutes, and will not let you speak freely.
Yulun? Question/comment. Is there any way that you can speed up the videos? Because I know that I think you have 3, and for the 3, a lot of the time you just stood there and didn't say anything. So if you made it shorter, you wouldn't have as much dead time. Is there a way to do that, or is there a reason why they're so long?
I can make it shorter. It's not a problem.
Levi?
Yes.
I would like to argue with you in the following sense. The long videos allow to attract attention and allow to give details of the of the processes. So maybe one can keep long videos and fill the whole period with explanation. Look here.
Yeah, yeah, and that's fine. It was just, I think this is the first time going through, so I just wanted to point out there was a